Good evening, friends and colleagues. My name is Jagadish. I am the President of the Australian Academy of Science. To commence this evening, I acknowledge and pay my respects to the Ngunnawal people, the traditional owners of the lands on which the Shrine Dome is located. I also acknowledge and pay respect to the traditional owners and the elders past, present, and emerging of all the lands on which the Academy operates and its fellows and staff live and work. They hold the memories, traditions, cultures, and hopes of the Aboriginal and Torres Strait Islander people in Australia. Today, during National Reconciliation Week, it is important to acknowledge the challenges in Australia's reconciliation journey and the shared responsibility we have to continue striving for better outcomes for the First Nations people. The Academy works hard to respect and celebrate the scientific contributions of First Nations people, integrating traditional knowledges for a stronger, more innovative, and sustainable future. Reconciliation between non-Indigenous and Aboriginal and Torres Strait Islander peoples is essential for a scientifically informed community. Embracing traditional knowledges will strengthen the nation, and building respectful relationships with First Nations colleagues and partners is key, aiming to empower the next generation of scientists through opportunities, listening, and partnerships. The Australian Academy of Science is committed to this. This evening, the Academy with the National Committee for Space Science and the Canberra Deep Space Communications Complex welcomes you all to the Shrine Dome. I would like to warmly welcome our speakers for this evening, along with Erika Olsen, the Charge d'Affaires and Acting Ambassador at the US Embassy. And I also welcome Academy Fellows who join us here tonight and all the friends of the Academy and of science in our audience. This evening, we'll hear from three distinguished space leaders visiting us from NASA's Jet Propulsion Laboratory. Dr. Laurie Leshin, Director for the Jet Propulsion Laboratory, Suzanne Dodd, the Director for the Interplanetary Network Directorate at NASA, and Amy Smith, RF Engineer at the Jet Propulsion Laboratory. And I look forward to hearing from you soon. I also had the honor of visiting Jet Propulsion Laboratory in 2018 under the Distinguished Visitors Program for a week. And I was truly impressed with the scale of things, innovative things which are happening at Jet Propulsion Laboratory. I'm very much looking forward to hearing from you most recent developments happening at the lab. The Australian Academy of Science has a long history of involvement with space science. Indeed, the very first of the Academy's scientific committees was the establishment of a committee on upper atmospheric research in the late 50s. This represented a significant leap in global scientific collaboration, allowing unique Southern Hemisphere researchers to collaborate on experiments from geophysics to astronomy, which continue today. And I've not forgotten about geochemistry, Director Leshin, and who is an expert in that. Historically, Australia and the United States of America have always shared a fascination with space. In 1967, Australia launched its first satellite with the assistance of the United States of America Redstone rocket. This mission measured solar ultraviolet and X-ray emissions and determined atmospheric molecular oxygen densities around the globe from observations made at sunrise and sunset. 2 years later, Australia was hosting NASA tracking facilities through the Deep Space Network, the space tracking and data acquisition and of course the manned spaceflight network tracked from Honeysuckle Creek, just 50 kilometers or 31 miles for our US friends from here at the Shrine Dome. The Academy is committed to supporting Australia's long-term future in space science through the vision set in the National Committee for Space Science Decadal Plan. Launched in 2019, the plan identifies Australia's biggest goals and priorities. In addition to the development and delivery of this decadal plan, the National Committee for Space Science fosters the space sciences in Australia, links the Academy to Australian space scientists and relevant scientific societies, and links Australian and overseas space scientists primarily through the Scientific Committee on Solar Terrestrial Physics and the Committee on Space Research. We are thrilled to have you with us tonight. Professor Phil Bland, the chair of this national committee, and Professor who is with us, and Professor Bland is the director of Space Science and Technology Center at Curtin University, and he joins us tonight as our MC. Over to you, Phil.
Thank you, Professor Jagadish. It's lovely to be here. It's lovely to have honored guests and all you attendees. I think tonight's going to be a real treat. I'm, as Professor Jagadish says, I'm chair of the National Committee for Space Science, and our remit really is to both reach out to colleagues around the world, like Laurie and her colleagues here, develop collaborations and connections with them, joint work with them on missions, and basically try and further the any way we can help the community of space scientists in Australia and spacecraft engineers in Australia. And it's a privilege to be able to work with these people and see kind of young people coming through and getting into that field. I really love that. So tonight is going to be a real treat. I think we've got a remarkable group of inspirational female leaders with us tonight, and I'm really looking forward to talking with them and seeing Laurie's talk, and then I get to basically just ask them questions for half an hour, which is going to be great. I'm going to begin with introducing Chargé d'Affaires Erica Olson as the first of our remarkable female leaders. Erica, I think, has been political counselor to such a range of nations that many of them I've never heard of, and speaks languages that so welcome, Erica.
Thank you so much, and it's great to be here with you this evening. I too would like to start by acknowledging the Ngunnawal and the Ngambri people, the traditional custodians of the land on which we meet, and I pay my respects to their elders past and present, and we thank them for welcoming us to this beautiful land. It's an honor to be here with you today and with these three extraordinary women from NASA's legendary Jet Propulsion Lab. Australia is no stranger to distinguished visitors from the US space agencies. In just the last year, we've hosted the NASA administrator and his deputy, the head of human spaceflight, and the JPL Deputy Director, who is now living in Melbourne, by the way. I'm always proud to be able to showcase America's achievements in space and highlight the deep and long cooperation between the US and Australia. But there's something particularly inspiring about the three leaders we have with us here today, because they show us what is possible when we invest and give women and girls an opportunity in areas where they have traditionally been absent. After all, Dr. Leshin is the first woman ever to head her organization in its 88 years of existence, but we all are very hopeful that she will not be the last. JPL was founded in 1936, and they didn't hire a female engineer until 25 years later. When Neil Armstrong first set foot on the moon, there was only one woman watching from the control room at Kennedy Space Center among scores of men. Even today, unfortunately, women continue to be underrepresented in STEM fields, comprising only 29% of the STEM workforce globally, and sadly, the numbers are even lower than that in the United States and Australia. Fortunately, our governments are working on closing this gap, and having inspiring leaders who show what's possible is such an important part of those efforts. The US Department of State runs a program called Tech Girls, where teen girls from around the US and the world gather in the US for a 24-week tech camp that also teaches how to access the pathways to STEM careers. The Australian Department of Industry, Science and Resources recently gave $41 million to fund 500 university scholarships for women and non-binary people. But education is only one part of the solution. One study showed that only 1 in 10 women who earn a STEM degree are working in the STEM industry 5 years later. That's why we need programs that break down systematic barriers, like the US National Science Foundation's ADVANCE initiative, which helps early career medical researchers offset the cost of childcare, or Tech Women, the partner to Tech Girls that I mentioned a moment ago, which places emerging STEM leaders from developing countries into mentorships at US companies. One of our hosts today, the Australian Academy of Science, authored a Women in STEM decadal plan that guides stakeholders on how to build the workforce of the future. And I look forward to watching it be put into action over the next few years. So too, the recommendations of Professor Lisa Harvey-Smith, Australia's recent ambassador for STEM. And beyond these specific initiatives to promote women in STEM, our two countries are also uplifting our commitment to science more generally. 1 year ago, President Biden and Prime Minister Albanese included in their joint leaders' statement in Tokyo a large focus on science and innovation, including the clean energy transition, building defense capabilities, harnessing emerging technology, reaching new frontiers in space, and building cyber capability and capacity all together. Australia and the United States have some of the brightest scientific minds in the world, many of whom I think are here today, but some of them are sitting on the sidelines, and we cannot achieve our shared goals of reaching Mars or transiting to net zero economies with one hand tied behind our backs. Projections show that both countries and many of our international partners will have large staffing gaps in the industries of the future. We need a bigger, more diverse STEM workforce taking new and innovative approaches. That means more women, more people of color, more workers of all kinds jumping into the pool. And we must engage earlier. As a mother of three daughters, I know that giving girls confidence in their math and science skills at a young age makes all the difference. My hope for my daughters is that by the time they're up on a stage like this or writing policy papers, that they don't have to brainstorm ideas to close the gender gap in STEM careers, because there won't be a gender gap to close. We won't get there without role models like Laurie, Suzanne, and Amy, showing young girls that it can be done, and it must be done. The US-Australia Alliance will be better for it. Thank you so much, and thank you so much for being here with us, and I look forward to hearing from you all. Thanks so much.
Thank you, Erica. I'm going to introduce Laurie shortly and the talk that she's going to give. I've known Laurie for quite a few years. I think it was 1997 when I first bumped into you. I don't know if you remember this, but it wasn't that long out of my PhD. You were driving somewhere in Maui, and just for so that people know, men also have imposter syndrome. I'm not going to blame it on you, but I definitely felt, can I really do this stuff? After I met you. So for what that's worth. Laurie is an inspirational leader and has had, as you can see in the flyer for the talk, many leadership positions as an advisor in the White House, in academia, in senior positions within NASA. But it should also be remembered that Laurie is one of the most accomplished scientists of her generation. She was the inaugural recipient of, of the NEAR Prize, which is the highest award in planetary science. I'm a planetary scientist, and made contributions in our field that are, the ripples of those are still being felt today. And I think fundamentally one of the things that helps make Laurie a leader in an organization like JPL is that everyone there knows that you're a great scientist as well, Nate. And I think, that's bound to be more engaging with the people that you're leading there. Before I stop talking and let you see Laurie's wonderful talk, I just want you to think about two things. One is I got a sneak peek, and part of it shows the reactions of members of the public and students and kids when with a Mars lander that everyone has seen JPL's success with. I want you to pause and think about what that means when we're looking at that. You're looking at the reactions of people here and in other countries around the world. That's a US federal agency achieving one of its key performance indicators. So consider that, consider how weird that is. We're cheering on a US federal agency there's something very special about space that means that it engages people all over the world. It's quite difficult to put your finger on what that is. But the fact that people, I am staying up to 3 a.m. to watch NASA land a spacecraft on Mars, I think says something very important. Finally, a lot of people, I think, incorrectly feel that science can be reductionist. The people that love it, and mostly the people that are good at it, know that it isn't. And I think for me, JPL embodies how science can and should be holistic and ask the really big questions. So that's it from me. Thank you, Laurie.
All right. Well, good evening, everyone. Hello, balcony people. Great to see you all. Thank you for coming out. It was very hard to get out of that couch thing, especially with as jet lagged as I am. I just was sort of, yeah. So, but I'm really thrilled to be here. And to the Academy, thank you so much for having me. And Phil, thank you for the wonderful introduction. And Acting Ambassador Olson, thank you for the wonderful words, very inspiring. I was raised by fabulous feminists, and so I'm right there with you that we have more work to do because we need all the brains to solve the big challenges that we have, and so creating space for that is so critically important. And it's wonderful to be in Australia. I got to spend the day today at our Deep Space Network complex here outside Canberra. And again, many members of that leadership team of our amazing partners here in Australia are here with us this evening, and they do incredible work. And you're gonna get to hear more about that with my colleagues who are here with me. So I'll come back and talk about it, but just to say that this partnership is very lengthy, really dates back to the beginning of the space age, and is still so foundational to nearly everything you're going to hear me talk about tonight, because we don't get to do the science if we cannot get the data down from our deep space missions, and that is not an easy task, and it is done 24/7 here in Australia, and just plays an essential role in us being able to do what we do, and we're so proud to partner with our colleagues here in Canberra. So a huge thank you to our Deep Space Network team here. Just had an absolutely thrilling day, climbed up into our 70-meter antenna, not all the way up, but far enough that It was high. Let's just put it that way. All right, so what I'm going to do is give you a very whirlwind tour of many exciting things happening at NASA's Jet Propulsion Laboratory, which is one of the NASA installations in the US, located in Pasadena, California. We are a slightly unique organization within NASA. You all probably know, Houston, we have a problem, so Johnson Space Center in Houston, or where we launch things. Most of the things come from Kennedy Space Center in Florida. Those are government laboratories where the employees are largely government employees, and JPL is a little bit different. We are a different type of organization where NASA operates, NASA funds us and owns sort of the land and the buildings, but the people actually come from Caltech. So we have a huge partnership with a university, a leading STEM university in the US, and that's a big part of sort of our innovative ethos, is that partnership. And so I'll just start with a little bit of history there. So JPL started at Caltech. There were faculty and students who basically kept blowing things up on campus. And here we are at the storied Australian National University. I'm sure that's never happened here, that any laboratory issues have happened. But basically in the 1930s, the thoughtful leaders at Caltech said, the mountains, they're right there. There's this nice arroyo, a valley. Why don't you go do your rocket engine tests up there? And JPL was born, basically because these guys got kicked off campus. So the gentleman reclining here on the left, that was the very first successful rocket engine test. That's the founding of JPL on October 31st, 1936. And the jet, we don't work on jets these days. We do a little bit of work on propulsion, but not very much. We are a laboratory, so that part's good. But that was because they had originally been working on rocket engines and were working on sort of strapping rocket engines to early jets to assist their takeoff, and that's really where the name came from. But pretty quickly, these folks went from trying to build rocket engines and rockets to thinking about the thing that goes on top of the rocket. And in fact, the founding of the American space age is on the shoulders of the people of JPL. And because America's very first satellite, which was the US's response to Sputnik being launched by the Soviet Union, that first satellite called Explorer 1 was built by JPL. And it discovered the Van Allen radiation belts and was the first scientific satellite in history. And we're really proud today to continue the tradition of the scientific exploration of space. So the gentleman on the right, and this was just about 20 years later that we successfully launched America's very first satellite, which led directly to the founding of NASA. So this satellite launch was on January 31st, 1958. Less than 6 months later, the US Congress created NASA. And less than 2 months after that, they moved JPL from being an Army lab to being part of NASA, where we have been ever since. So we predate NASA, we've been with NASA since their founding, and we're a little bit of a special flavor of NASA installation. And we're very proud of our history and of our structure as being a little bit different. Now, the ambassador mentioned that it took a few decades for JPL to start hiring women engineers. And you might think from these pictures that there were no women around from very early on. And that actually is not true. While we didn't hire women engineers initially, there were technical women who were working side by side with the men from very early on. These were the women computers of JPL. And they, I don't know if you got the movie Hidden Figures here. Did you all see that? So that was about NASA Langley, which is a NASA center on the east coast of the US, and about the women computers who worked there. And they worked shoulder to shoulder with the men. Most of these women studied mathematics in college. They were brilliant minds. And the men were building rockets, early rockets and early satellites, and the women were telling them how to launch them and where to point them, essentially, because they did incredible calculations to predict the trajectory of the early rockets. So, for example, this woman in the upper left is tracking and projecting the path of the very first interplanetary flyby, which was Mariner 2, by Venus in 1962. So as was already mentioned, I am the first woman director of JPL in our 88-year history. And so I think every day I think we all owe a lot of gratitude to the people whose shoulders we stand on. And I think about these extraordinary women whose shoulders I stand on. And I'm pleased to share that today, the women of JPL number over 2,000. Including not just the director, but the deputy director and many other incredible women leaders across the lab. So we're very, very proud of these women that really blaze the trail for all of us to come later. So what do we do at JPL? So this is kind of our universe, right? We work in three main science areas. In astrophysics, in planetary science, which again, we're very well known for our Mars rovers and things, and I'll give you some examples in each of these areas. But we also work in Earth science, we study our home planet, and of course, deep space communications, which is a huge challenge, and we are the world leader in that, again, along with our partners around the world, including, very importantly, here in Australia. But this is another way to look at it. I call this our family portrait. So these are the missions that we're working on today at JPL. So they're either, if the letters are in bright white, that means they're already flying. If they're a little bit more grayed out, that means they're getting ready to fly. So we're working on them on the ground. And you can see the huge variety of activities that we're involved in. It's one of the most exciting things about my job. When I met earlier today with the staff at the Deep Space Network complex, and I said, one of the things I love about this job is that I get to, like, if I ever have to just sort of spontaneously stand up and give remarks, I can just talk about all the things that happened in the last week and fill 20 minutes because, we shipped this here, we launched that, last week we literally launched a mission from New Zealand, shipped something to another NASA center across the country, delivering an instrument, which I'll tell you about. We also shipped Europa Clipper, our next big interplanetary mission, to Florida to get ready for its launch. So every week is a crazy busy week and so exciting. So we work on missions like in the middle towards the top there are the large space telescopes that we participate in. So we didn't build the James Webb Space Telescope, but we provided one of the sensors on board, one of the major instruments on board James Webb. And we work on many other astrophysics missions that are trying to understand the origin and evolution of the universe and also look for other solar systems. We have spacecraft, we are the only institution in the universe, as far as we know, to have visited all the planets in our solar system. And we have many spacecraft today at various destinations across the asteroid belt, at Jupiter, of course, our fleet of missions at Mars. But I think the thing that people don't realize about us that is incredibly important is the work that we do to understand our home planet of Earth, right? Applying the same kind of innovation and know-how that we use to explore deep space to understand how our Earth is changing. And I'll give you some examples of those things, but you can see how many missions we have either already flying or in development to study our home planet. And actually that's where I'd like to start. So I'm just gonna give you a few examples in each of these areas. So one of the first big missions we launched when I arrived at JPL, or after I arrived, is a mission called SWAT, which is all about studying water, Earth's water, life-giving water, right? Such an important thing to track and understand. And we have been seeking to understand the seas and how they are changing. We've been tracking sea level rise for a long time, but with SWAT, we're doing so with new resolution, new precision. When you have very high resolution in tracking the height of the oceans, it means you can snuggle up right to the coasts and understand what's happening with sea level rise right at the coast where it impacts people. And then the other big thing that SWAT is doing for the first time ever, it is tracking fresh water on land. Today, before SWAT, if you wanted to know what was happening with lakes and rivers around the world, we have stream gauges, basically, and lake gauges in maybe 1,000 streams and lakes around the world. Well, SWAT every 21 days measures the height to better than an inch of millions of lakes and rivers all over the world. So we are now tracking fresh water on land in ways that we've never been able to in the past. And this is just one example, a local example for us in California. You might have heard we've had a lot of rain. I promised my husband when we moved to Southern California that he was going to love the winters. It rained 25 inches at our house the first winter. Now, I'm not complaining because drought is terrible, and we had been in that, as you all have as well. But we had these atmospheric rivers. Here you can see some land flooding, again, comparing between just a few weeks apart, areas that are flooded. And so, again, you can use it for understanding sort of flooding and disasters. You can use it for understanding water management. And the applications of SWAT are just truly endless. We're so excited about this mission that is revolutionizing the way that we understand Earth's water from space. And what SWAT has done for water, our next big Earth science mission called NISAR is going to do for our understanding of land surface, of solid surface, of ice. So NISAR, so here's the cool part, I'm going to let you in on a little secret. One thing we love at NASA is embedded acronyms, acronyms within acronyms, because that's how we roll. So NISAR is a great example. The NISAR acronym stands for NASA, N stands for NASA, so acronym and an acronym right there. It's our first major joint mission with the Indian Space Research Organization, ISRO. So NASA, ISRO, synthetic aperture radar. So it's embedded acronyms there. And the single largest technical collaboration between US and India is this joint Earth science mission, which is a dual band radar system. That's a 12-meter reflector you see deployed there. And NISAR is getting ready to launch later this summer, and it will study, and I'll show you, I'll go to the next one, which shows you, that's the spacecraft in the clean room in Bangalore, India, with our integrated team working to put the final touches on it. It is going to help us understand how Earth's land surface is changing from things like volcanoes and earthquakes. How I wish we'd had NISAR up there with this latest eruptions in Iceland, right? Like they were thinking eruptions were happening and then they started happening, but we would be able to be observing the land surface change leading up to volcanoes erupting. After and potentially even before earthquake ruptures, really understanding how the Earth's surface is changing. Also with NISAR, we can track small changes in ice surface. So again, contributing to our understanding of how our planet's changing with climate change, and also biomass distribution. So understanding how the forests above ground biomass is changing on our planet. So it's an incredibly sensitive set of sensors, and we're very excited to get it launched and flying. So stay tuned for NISAR, and you know the secret of the acronyms within the acronyms that of the name of the mission. So those are just a couple of examples of exciting things happening in earth science. I will say the other big thing we focus on besides water and things like earthquakes and volcanoes, we also are very focused on greenhouse gases at JPL and are currently flying on the International Space Station a sensor that's detecting methane leaks from things like pipelines, and methane is a huge contributor to greenhouse warming, and it's one of the ways that we can actually have a near-term impact on global warming is if you find methane leaks and are able to stop them, because the methane residence time in the atmosphere is quite short. So if you can stop the methane emission, you can actually pull methane out of the atmosphere very quickly. And so again, we're excited about our contributions to understanding and mitigating the impacts of climate change. So now let's go out into space and talk a little bit about the next big astrophysics mission that we are working on. So you all know about the James Webb Space Telescope. What an incredible, incredible observatory. The next great observatory that NASA will launch is called the Nancy Grace Roman Space Telescope, named for a woman. Very cool, not very many satellites named for women. It might be the first major NASA one. So Nancy Grace Roman was called the mother of Hubble. She was the director of astrophysics at NASA when there were like no women in leadership at all. So she was a real pioneer in her day. And this space telescope is going to be mainly focused on cosmology, on questions about dark matter and dark energy, these things, these fundamental characteristics of the universe that we really don't understand very well at all. But the truth is, and we do a lot of cosmology research at JPL, and we're very involved in that part of the Roman telescope, but one of the big driving questions for our deep space exploration at JPL is kind of what I would call the biggest question that a scientist can ask, which is, are we alone in the universe? And I believe that we are on the precipice of being able to answer that question. And there are a lot of different places that answer could come from. And frankly, we're in kind of a space race with ourselves to see where that answer is going to come from. Is it going to be from Mars? Or is it going to be from one of the moons of Jupiter? Or is it going to be from a planet orbiting another star? Where is that evidence going to come from? And the Roman Space Telescope is going to fly a sensor on board, an instrument called a coronagraph, which is going to help us get to the point of being able to answer the question about planets around other stars. So let me just show you a little picture of this thing. That is the sensor itself. It's about the size of a grand piano. It's very large, highly sensitive optical instrument. So how do you do this? If you want to take a picture or measure the light from a planet around another star, the problem is that the star is very bright and the planet's very dim. So you have to block the light of the star really, really well. Like, you need to be able to think about it if you wanted to see a single firefly at the base of a lighthouse. Like how well you can block out the light of the lighthouse to see the very faint single firefly from pretty far away. So a coronagraph is the thing that does that. It blocks the light of the star really, really well so you can see those really dim planets. And in fact, this little cartoon here is our demonstration of the fact that, in fact, this coronagraph is going to meet our requirements to block the light incredibly well, to be able to see Jupiter-sized planets around nearby stars. Now, what we'd like to be able to see is Earth-sized planets. That takes even 2 orders of magnitude better blocking of the starlight than this instrument's going to do. But this instrument is a huge leap forward, and it's going to teach us so much about how to do that on the next big observatory, which is going to be called Habitable Worlds Observatory, where we'll get to be able to image those Earth-sized planets. We're very excited about where this mission is going to take us, and again, within a few years, this mission will launch at in 2027, 2028 or so. We will soon have, again, family portraits of other solar systems, thanks to this coronagraph instrument, and eventually, hopefully, maybe see signs of life on some of these other planets. That probably won't happen with this mission, but the one that comes after it. And this is paving the way technically for that. Coming to the solar system now, kind of in many ways, the bread and butter of the work that we do at JPL. We have many different missions underway. One is a mission called Psyche, which we launched last October, which is going to explore a whole new kind of world. Think about it. We have been to rocky worlds like our moon or Mars. We've explored gas giant planets like Saturn and Jupiter. We've explored icy moons of those planets, so ice worlds. We have never explored a metal world. And Psyche is on its way to do just that. It's going to visit an asteroid, also called Psyche, just to keep everybody on their toes. The mission's called Psyche, and the asteroid's called Psyche, so you have to say Psyche mission. Or asteroid Psyche. So Psyche mission is going to visit asteroid Psyche, which is one of the highest density asteroids we know about, and we're excited to see what it looks like. Here's what an artist thinks it's going to look like. It's definitely not going to look like that. We don't know what it's going to look like. It's pure exploration, right? We're going to get out to this asteroid in 2029 and go into orbit around it and map it for several years. Here's what the spacecraft looks like in real life. And yeah, there's a cat video story that I'm going to tell you right now. So Psyche, again, launched last October. It is on its way to an asteroid. In addition, and this happens a lot actually at JPL, in addition to sort of the core science mission that we're trying to do, we also try and fly new technology. something that's going to break a barrier so that next time we can do more. And on this mission, we're flying something, this little tube you see at the bottom of the slide here is a little telescope for a demonstration of optical communication or laser communication from deep space. It's called the Deep Space Optical Communications Experiment. And it is kind of the next leap forward. Obviously, we do our F-based communication at the Deep Space Network site here and those around the world. But we all believe there's a huge future in moving to optical communications where you can send down much higher data rates, and especially from deep space. This is it's a big limitation for the amount of data that we can get. We design our experiments so exquisitely carefully not to exceed the bandwidth we have, and our fabulous folks at the DSN are always trying to get us more data, and we always want more antennas and more hours in the day that we wish we could be downlinking. But so the Deep Space Optical Comm experiment successfully now, from 80 times further away than the moon, broadcast at 267 megabits per second. So that's pretty good broadband speed, right? So that's not bad. And it broadcasts this cat video. Because why wouldn't you, really? I mean, honestly. So this video is actually of the cat of one of the team members, and is the first broadband video to be broadcast from deep space. So this is a super famous space cat now, named, I should remember this. Taters, thank you, Susie. Yes, the cat named Taters. And imagine though, I mean, I want full HD video from the surface of Mars when our first astronaut sets her boot into that red soil, right? I want that high bandwidth communications that we're going to need. So this is a very exciting thing as well, demonstrated just this year. And then coming up next in deep space is, I'm so excited about this one, Europa Clipper, our next big launch for deep space mission. So Europa Clipper, it will launch in the launch period starts October 10th. And just last week, we shipped Europa Clipper from JPL, where it was built and put together, to Florida, where it's getting ready for doing its final launch preparation. So what is Europa Clipper? So Europa is a moon of Jupiter, and it is an icy moon. So its surface is water ice, solid water ice. But we believe, based on a lot of lines of evidence, that underneath that icy shell is a global ocean of liquid water. There's twice as much water in this ocean as in all of Earth's oceans combined. It's a lot of water. And on Earth, wherever we find liquid water, we find life. And so the question is this a habitable environment? Who would have ever thought a moon of Jupiter could be a habitable environment? But we are going to go and try and find out with this extraordinary spacecraft. And I'll tell you why this is hard. First of all, Jupiter is very far away, so 5 times further from the sun than the Earth. It's a solar-powered mission, as you can see in this animation. That's hard to do that far out. So the solar arrays are gigantic, would basically spread and reach across this entire room. It'll be the very largest thing we've ever sent into deep space with those large solar arrays. Has 9 different sensors on board to be able to sense everything about this moon and try and understand how thick is the ice. Are there places where that ice gets thin? Is it spewing material into space? If so, let's taste that and understand what it's made of. All kinds of different scientific things happening. And they're happening in what is the harshest environment in pretty much the entire solar system. Okay, except if you sort of fly right up next to the sun, that's pretty harsh. But anywhere else, this is the nastiest place to be. Every time this mission does a close flyby of Europa, it gets a radiation dose equivalent to 100,000 chest X-rays. And it's going to fly by 50 times in the course of this mission. And that's why we don't go into orbit around Europa itself. We're going into orbit around Jupiter, and we're going to fly by Europa over and over again. Let me just show you, by the way, what this thing looks like. Here it is in our clean room, getting tested a couple of months ago. But we fly by, we fly in close to it and get that terrible radiation dose. And then we fly a little further out for a few weeks and just chill, right? and heal a bit from that radiation dose. So that's why the mission's designed the way it is, but we're going to get a global map of Europa over the course of the mission and really grow to understand whether this could have been a habitable environment in our own solar system. So that's one possibility of a place we could find life. And the next is really at Mars. And I'll wrap up by talking about Mars and then a few other things at the end here. But Mars has been a real center of fascination for me personally since as a 10-year-old girl, I stood in my mother's kitchen and saw the very first images from the Viking landers when they landed in the mid-70s. I grew up in Phoenix, Arizona. I think it kind of looked familiar to me, honestly, Mars, you know. There are parts of Australia that I think look kind of Martian too, right? I definitely wanted to reach out and touch those rocks. And that fascination and the possibility that life could have gotten started on Mars early in its history is really what has been driving so much of our Mars exploration program. And the most recent additions to that program are a rover called Perseverance, which landed in February of 2021 in the middle of the pandemic, right? Remember? I wasn't at JPL at that time. I was president of a university in Massachusetts, and I was pacing around my kitchen because it was COVID, so we were working at home, and I was so nervous about it. And after we landed, JPL landed successfully on Mars. I went outside and just looked up at the sky and started to cry, because you remember what we as human beings can do in spite of this incredibly challenging moment that we all found ourselves in. And so I put in this video for Perseverance's landing because I'm super inspired by the reaction of people all over the world in this really tough time. So let's just watch this.
Propulsion, go. EDL safely, go.
We have deemed Perseverance ready to execute entry, descent, and landing on her own. Confirmation of entry interface. Perseverance is currently going 5.3 kilometers per second, about 120 kilometers from the surface of Mars. It will start controlling its path to the landing target. Parachute has deployed, and we are seeing significant deceleration. The heat shield has been separated. Perseverance now has radar lock on the ground. The back shell has separated. Skyframe maneuver has started, about 20 meters off the surface.
Tango Delta, nominal.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the sands of past life.
Pretty good, right? So here she is, for real, on the surface of Mars. So that's Percy, as we call her. And her little friend there is Ingenuity, the small Mars helicopter that we also delivered. So Ingenuity was tucked up underneath the belly of the rover and then deployed about 6 weeks after we landed. And Ingenuity is another example of a technology demonstration where we wanted to, so I'll come back and talk about Percy in a second, but let me just talk about Ingenuity for a minute here. It was another occasion where we wanted to try and push the envelope. We have a core science mission with Perseverance. And we also thought, well, what's the next big thing in Mars mobility? What's the next big idea? And we think it's to take to the skies. Now, this is a crazy idea because the atmosphere on Mars is so thin, it's the same density as it is on Earth at 100,000 feet. Helicopters on Earth only fly to 20,000 feet. This is impossible to fly a helicopter on Mars. And yet, some people really stuck with that idea and brought it to life, and we were able to get it flown to Mars. Now, it was only supposed to fly 5 times. If it flew once, it would have been a miracle. It was only supposed to fly 5 times in 30 days, and all kind of in the same position, like in the same place, not really fly around very far. It flew 72 times, lasted for 3 years, and flew 10 miles. And instead of, with Perseverance, it was non-interference. Like, this is a technology demo. You can't interfere with the science mission. Ultimately, Ingenuity scouted the way for Perseverance in those 72 flights, flew ahead and kept ahead of the rover, and was able to communicate back with Earth through the rover. So we just said goodbye to Ingenuity a few weeks ago, because finally, after 72 flights, she had a hard landing and busted her blades. But it was truly an extraordinary accomplishment. It's a Wright brothers moment. It's it's that equivalent of a huge first. And in fact, the flight spare for Ingenuity is now in the Smithsonian Air and Space Museum, actually the Udvar-Hazy Center in Washington, D.C., if you're ever there, and you can get a chance to see the giant space shuttle and the tiny 4-pound Mars helicopter. So very proud of that. And Perseverance is still going and has driven for tens of kilometers already across the Martian surface, and it is doing an incredible job exploring a place that we believe used to be a lake. It's a dried up lake bed. We know that Mars had water in its past. Today, the surface conditions are not very hospitable for life, but we know in the past, at the same time that life was emerging here on Earth, that Mars also had very nice conditions for life to emerge. And so we want to understand whether that happened. And so Perseverance's job is to drive around and sample different rocks that might preserve that evidence. And here's one of the most recent ones it just collected. This is for the rock geeks in the room, my friends. And I know at least 2 of you here, and there are probably others. But this is exactly what we came to this crater to find. Silica cemented carbonates. It's exactly the kind of rocks on Earth that if there are fossils around, this kind of rock can preserve them. This is jackpot. This is just what we're looking for. But in order to determine whether there are fossils or chemical fossils or physical fossils inside this rock, we have to bring it back to Earth. We've got to get it into labs at places like ANU that will allow us to tear it apart atom by atom and understand it at incredibly high resolution to be able to truly know whether or not life got started on Mars. So our next big challenge is to do the round trip. We've been to one way to Mars many times now. Now it's about, can we go and come home? So bringing these samples home is our next big challenge at JPL, Mars Sample Return Mission. I'm just gonna wrap up by talking about the incredible partnerships we have with Australia. Again, I just had the thrill to be at the Deep Space Network complex earlier today, and to just meet with the extraordinary team and to see the incredible, beautiful, by the way, first of all, if you haven't been there, you should go, installation there. And every single day, not only do the folks at Canberra operate this complex, they operate our other 2 sites around the world as well. So the Deep Space Network, for those of you that don't know, they are the people responsible for talking to everything beyond basically geosynchronous orbit. And they have to do so from 3 different places around the world, right? Think about it, because if you're far flung out in the solar system, you could be off in any direction, or Mars could be anywhere, or Jupiter could be anywhere. And so we've got antenna sites at 3 different places, one in California, one in Spain, and one here in Canberra. And during the day in Canberra, the folks here operate the antennas at the other 2 sites as well as their own. So truly incredible, incredible folks, and we're celebrating 60 years of that collaboration. We love it for science missions, but in addition, the DSN complexes are critical to future human exploration of the moon. We already have worked on the initial Artemis test flight, which didn't have any crew on it, but Artemis 2 will have crew on it, and Artemis 3 is meant to take humanity back to the surface of the moon, and those first words and first steps will be coming back through, as they did in Apollo, will be coming through the Deep Space Network, and very likely to be here, so that we're very excited about that. And again, huge gratitude to the team here for the great hospitality and the incredible contributions over 6 decades. They're celebrating 60 years coming up soon. We're talking about missions. You know, I think one of the things I love is this Deep Space Network collaboration has really laid a strong foundation for space involvement in this great nation, in Australia. And now you have a space agency too, and we're talking with them about, you know, multiple opportunities to collaborate on future missions. We are working with CSIRO on something that would apply some of the capabilities we have for instrumentation to challenges here in Australia. So this is one called AquaWatch, which is an imaging spectrometer meant to work on coastal regions and understanding their health. And so we look forward to lots of future opportunities as the space agency gets up and going as well. And then lastly, that next generation, preparing the next generation, is so critically important. It's so exciting to me to see great academic programs here across Australia really booming in space science and engineering. And we want to help with that at JPL. And one of the ways that we are is we've started a fabulous program jointly, which is to bring Indigenous interns to JPL. And we've had, I think, 3 groups now that have come, getting ready for the next one. And just what a thrill to be able to collaborate on getting a true, authentic NASA space experience for fantastic Indigenous STEM students here in Australia. So very proud of this program and look forward to continuing it and trying to help expand it across NASA as well. So we started at JPL, but now we're working with other NASA centers as well so that they can also welcome interns. So I'm going to stop talking now, and you're going to get to hear from a couple of my fabulous colleagues who work on the Deep Space Network. But Susie Dodd, who's here with us tonight, who oversees all of our interplanetary communication activities, also has a side job. It's kind of a side hustle. She's the Voyager project manager. Yeah, I know, right? Coolest side hustle ever. Well done, Susie. And you may have been reading that, do people know Voyager? I mean, people love Voyager, right? People know Voyager. Okay, so Voyager is very close to the heart of a lot of us. I use this slide usually as my last slide when I speak because I just feel like it's, to me, one of the true joys of this work is the sort of long arc of the impact of many of these missions. I call them modern cathedrals. Something like Europa Clipper has been thought about and dreamed about for decades, been taken 10 years to build, and now will take another almost 10 years once it launches to get to Jupiter. These things are career-long endeavors for many of us. Mars sample return, oh gosh, you don't even want to know how many decades we've been trying to get that mission flown. But Voyager is the best example. It launched 47 years ago in 1977, and they are both still going and still sending back data. They are the farthest flung human-made objects in history, and we still talk to them every day, and we talk to them through Australia every single day. It takes 22 and a half hours for the light. When we talk to Voyager, it takes 22 and a half hours for that light to get there. And when it talks back, very faintly, because it's very far away, 22 and a half hours coming back. And it's still telling us about the universe. It's literally the first thing that's sending back data from beyond our solar system. It has left our solar system at this point, and these things are so inspiring. So Susie is going to tell you about how she single-handedly saved Voyager 1 recently. No, it was a huge team effort, but she leads that team. And Amy is here too, who helps run the Deep Space Network complexes across the world and build those out. So I'm honored and thrilled to have incredible women colleagues here with me. So happy to get to speak with all of you and look forward to our conversation. I hope that was interesting to hear about some of the exciting things happening at JPL. And again, I really want to thank you all for listening. You want me to just go here now? Okay.
Thanks so much, Laurie. That was wonderful. I'm going to ask Susie and Amy to come up now. You gave a great introduction. Thank you so much. Susie is, in addition to her role as director of the Interplanetary Network, which kind of oversees the Deep Space Network, like Laurie says, is program manager. Is that right? Or have I screwed that up?
For Voyager?
For Voyager,
Project
yeah.
manager,
Project manager, but it's now called the Voyager
Interstellar mission.
Right? So just think about what that means, right? That's the Voyager Interstellar mission. That's okay, that gives me goosebumps every time I think about it. And Amy is involved in the construction, is overseeing the construction of 35-meter dishes around the world that allow those signals to come back. So this is just remarkable. Thank you so much for being here. All right, so now I get to ask a whole bunch of questions, which is lovely. So,
And I get to ask questions too, yeah?
yes, absolutely.
Okay.
Yeah, but I do first.
You get to go first.
So,
Okay.
Laurie, you mentioned with the Viking, you remember seeing that from Phoenix. My equivalent was Voyager, actually,
Yeah.
and I remember really clearly seeing those spacecraft go up, seeing that, and they were weird-shaped rockets, and it was just looked really different. And they had those great big fairings on top. But that's just stuck there in my mind, and I think, for me at least, both Voyager and also Apollo, that was a large part of why I became a scientist. I think it was just what happened there and then what those missions did. That was kind of same kind of thing for you with Viking?
Viking, yeah. I was alive during Apollo, but I really don't remember it. And it's funny, actually. I will tell the story very briefly, but reporters would sometimes ask me, what got you into science? And I said, I remember seeing the pictures from the Viking mission on the cover of Time magazine. And I said this once to a reporter, and he called me back 3 days later, and he's like, yeah, I checked. They were never on the cover of Time magazine. And I was like, what are you talking about? Of course they were. I have this very vivid memory that they were on the cover of Time magazine. I was standing in my mother's kitchen, and he's like, maybe National Geographic, it was on the cover. No, we didn't get that. We got Time magazine. That's what we got. And sure enough, he was right. It was because there was a very famous gymnast in the summer of '76, Nadia Comaneci, for those of you that are older like me. That's why I didn't read Time magazine as a 10-year-old. But I did pick up that issue because it had this gymnast I was obsessed with. But I didn't remember that. I remember on page 23 were the pictures of Viking. So yes, and they just transfixed me. I was fascinated ever since then. Yeah.
Suzanne, Amy, do you have a formative moment in terms of spaceflight when you were young?
Well, I think for me it was Apollo, I was excited by watching the astronauts, but I was also really excited by watching the capsule land in the ocean and the frogmen jumping out of the helicopter and rescuing them. But that was kind of my first taste of exploration, if you want to have it that way, and adventure, and that got me interested in studying math and sciences. Being the Voyager project manager, people always ask me what it was like, and I was a teenager when Voyager launched, and I honestly wasn't paying much attention to it. I was trying to get my driver's license, and but certainly when I got to college and they were making the encounters with Jupiter and Saturn and getting all that great data back, that stuck with me a lot. And it also brought me to JPL because I was able to get my first job working on Voyager for the Uranus encounter, and I stayed for the Neptune encounter, and it was just, JPL's a one-of-a-kind place, worldwide, first, Laurie just talked about all the firsts that we do at the Jet Propulsion Laboratory, and that was the place I wanted to work.
Thank you. Amy, do you have, yeah.
I actually came to JPL purely from my technical and engineering background. I didn't grow up watching I'm sure I saw bits and pieces of the space program, but it was not a place that I aspired to come to my whole life. I was really excited when I interviewed at JPL about kind of the overall mission, right? The opportunity to build things, to explore the solar system purely for the sake of science and for the sake of sharing that science with the world. And I've always found that just absolutely amazing that I get to work on work at a place that's the mission, right? The mission is bringing this information back for the sake of humanity, so.
That's wonderful. Thank you. Okay, so a contentious one. Favorite missions, and feel free to criticize one another's choices.
That's not contentious. I have the answer.
Yes, please,
Voyager.
obviously. So, I mean, I'm a big, so I'm not allowed to have favorite children, right? I cannot pick a favorite, but, I'm on the team of the Mars Curiosity rover. My friend Penny King is here somewhere. There she is, hey. She's on that team as well. We got to, it landed on Mars on my birthday in 2012, which was awesome. I was also live on CNN when my Mars mission crashed, an earlier one, and it's way more fun when they work. I will just say that, first of all. Second of all, it was just an extraordinary thing. We lived on Mars time for the first 90 days, so Mars day is 40 minutes longer than an Earth day, and so we kind of came to work 40 minutes later every day for 3 months. And the team got to be, unlike in the case of Perseverance, unfortunately, because of COVID, our team for Curiosity, when we landed in 2012, we co-located for 90 days in Pasadena at JPL. I wasn't working at JPL, I was a dean at a university in New York. And we all came together for 90 days and lived on Mars time. And every day you go to work, whatever crazy time of day it was on Earth, it was the same time of day every day on Mars, you would get the data down through the DSN from what your rover did while you were sleeping. It was awake. And you get the data down, and every day it was like, holy cow, what is this? What does this mean? What do we? And then you have to figure out over the course of the next 8 to 10 hours, what are we going to do next? Because now the rover is sleeping and we're awake, planning its day for tomorrow. And at the end of that day, you've got to tell it what you want it to do next. And the thrill of that, it was thrilling. And every day you're seeing something that no human has ever seen before. And to be able to do that is just, it was a huge privilege, first of all, but it was so exciting. So that personal experience of getting to work closely and knowing that scientists everywhere who get involved in these missions get to have that kind of experience is incredible.
That's a good one. Okay, Amy, what would yours be?
I think definitely the Mars missions, right? Like landing something on another planet is terrifying and exhilarating, and every time I watch a movie like the one you showed, it makes me tear up because it was just so emotional, the amount of work that everybody puts into these missions, and it's your heart and soul for many and many years of your life, and it all comes down to that 7 minutes when it's either landed or it hasn't, and you have to wait and find out. So it's absolutely thrilling.
Nothing you can do.
No. Guys, I think it's really helpful to people who who aren't scientists and who don't have the kind of jobs that you do, to get a sense of, okay, what is a kind of day in the life for you? What does an average day look like? I mean, at least for me, a huge amount of it is exhausting bureaucracy. And there's like maybe 2 minutes when a PhD student comes into my office and I remember why I started science. But what would a day in the life look like for you, Laurie? Or Amy, you start. Yeah.
So a day in the life of the DSN is, it starts with talking to our partners at the other sites, right? So we're always checking in with our Goldstone complex or the complex in Spain, the complex here. It's a lot of coordinating between the technical folks that are building the things that we're going to deploy out at the sites. And then interfacing with our JPL colleagues or our NASA colleagues. It is a lot of meetings, of course, but it's also a lot of exciting events where you get to, talk about the things that we do, where we get to explain it to other folks at JPL or other folks in the public. But lots of meetings, just like everywhere else.
Susie. Cool meetings. Yes.
Yeah. So it is a fair amount of meetings, but it's also, I think, as a project manager for Voyager, we interface a lot with NASA headquarters, our funding organization, so keeping them informed on how the mission is going, and making sure that we're following a schedule, and communicating back and forth with NASA, with my boss, Laurie, with the management at JPL. What's the status of the project? Is it going well? Do you need help? And Voyager is a good story, right? It's a great story for NASA. So we want to make sure that NASA has the correct story and can use that for publicity or whatever else they need to help support NASA just with the general public. And you have those days where you're tired, you're frustrated, and then you'll get an email from a 6-year-old in Germany who has designed Voyager 3 with a gigantic vacuum cleaner so it can suck up the dust that's in interstellar space, and it just makes your day, right? It just makes your day to have someone somewhere around the world know what you're doing and you feel like you've made an impact.
That's lovely.
That's awesome. So, I mean, as the director of JPL, there's no day is the same, which is very exciting because there's always something new happening or new people to talk to. And I certainly do a lot of public speaking and welcoming groups, and we're in LA, so like movie stars want to come visit us, which is kind of fun. So that's kind of cool. But you know what, honestly, I realized pretty recently, actually, the best experiences that I have had in my career have been those moments when magical things happen in a team. And so when Curiosity landed, that was one of those moments. I've been involved in other team-based activities at JPL earlier in my career where I was leading a mission team, and it was like when things go well, like when things are really moving forward, and even if you're struggling with something really hard, but you're doing it with an incredible group of people who respect each other, have diverse backgrounds, smart as heck, but trying to solve something nobody's ever solved before, like it's magic can happen there. And it occurs to me that my job is to clear crud out of the way so that magic can happen in those teams. And I think so much of what we do as leaders is about that. It's about trying to clear the way. So I literally started something at JPL called the Snowplow Team. Their job is to run in front of our project teams and clear crud out of the way so that the project teams can do the magic that they need to do. And if you don't always succeed in the bureaucracy, of course, but even if you can succeed a little bit and make it a little bit easier, a little bit more magical, I think that to me is the best, legacy that a leader can have, is they made it a little bit better for people, right? To try and make that magic happen.
That's lovely. I think, okay, so that's actually an opportunity for me to ask a leading question that you
Yeah.
don't need to answer, which
Cool.
is now, I think, in my opinion, that one of the reasons that nations have science-based agencies, space agencies, is because it is a great model of bringing together in a team, your brightest and best scientists and the brightest and best engineers, and setting them an incredible challenge.
Yeah.
And then so much great stuff flows from that. It's my understanding that, there was an independent study for NASA that showed that there was a ×3 roughly return on investment. So $1 in.
Sure.
Got, yeah.
Economic impact is
Right,
huge. Yep.
economic impact. So, imagine like you're an individual and someone says they'll give you 3 times return on investment in a year. You'd think that's going to be a con, right? But I think that's what NASA does for the US. So why would a nation choose not to do that? I mean, that seems like a really weird choice for a nation like ours to make. So that's the leading part.
Yeah, thanks.
Yeah,
Okay.
that's right. You don't
What's
have
the
to
question
answer
part?
that.
No, look,
yeah.
I mean, here's what I would say. We're seeing extraordinary interest in space exploration. It's such a fascinating moment for the space ecosystem, right? I mean, at some level, we have it easy at JPL. We were first, like literally first in the US, right? And so it's easy to lead when you're the only one. But now the space ecosystem has gotten so diverse and so interesting that it's more complex. And one of the things we're seeing with things like the Artemis Accords, so this thing that NASA started to try and help get international interest in exploration of the moon and really setting the stage for that future exploration. We just have the 40th signatory of the Artemis Accords. It's an incredible opportunity for diplomacy, for economic growth, and also for scientific discovery. And so we're seeing huge interest on the commercial sector, huge interest from brand new international space agencies that are starting all over the place. And I think they're all trying to figure out what their niche is and what they're like, how to play. And that to me is just opportunity for excitement. But I absolutely agree that one way that we need to continue to leverage the possibility of space is by trying to do really hard things.
Yeah.
Not, all space is fun, like don't get me wrong, it's great. But if we're not constantly trying to push ourselves to drive new discovery, to try new things, then we will lose some of that magic of space. And those things are hard. The James Webb Space Telescope, almost impossible. Mars sample return, the first round trip to Mars, really, really hard. And yet, to answer the big questions, you have to do really hard things. And so I think, I'm with you. I think science leading the way is very exciting.
The way, so at the top of Laurie's talk, dare mighty things is JPL's motto. And I think that kind of encapsulates it. If you think about it, you can give scientists and engineers a target and say, look, build a better radio. But if you say, we need a spacecraft that can communicate data on the possible existence of life on Mars from, that far away, you get, a whole bunch of brilliant young people stretching, everything they can to meet that goal. And simply putting that goal in front of them is how you get incredible results from daring mighty things.
You have to be willing to fail sometimes.
Exactly,
too, right?
absolutely.
Like otherwise you're not daring mighty enough thing.
Exactly. I'm really interested in kind of one of the things that came up in your talk. A thing that struck me a few years ago was a comment that Michael Collins made. So Michael Collins was command module pilot for Apollo 11, and he said that on the world tour that they did, no one said, this is a great thing that America has done.
Yeah.
Everyone said, this is a great thing that we have done. Yeah. And there's this really interesting, we think about space as this almost kind of uniquely inspirational thing, But it is also somehow, you know, as you showed with all those people clapping and just super excited all over the world, it really unites people. I mean, what do you think that magic is that causes that to happen?
I would think you should, I mean, Voyager, I think, is one.
Yes,
Yeah,
absolutely. yes.
Really.
I think I get asked this question frequently, and I have to think about it frequently, and maybe as I get older, my opinions have not so much changed, but just gotten more to it's that sense of adventure. I think Amy was talking about that too. What's out there? What could be out there? What could we do? We're the pale blue dot in the universe. You know, are there aliens? Will they talk to us? Will they play that gold record? You know, will they know what a phonograph is? So it's that sense of adventure. It was once described to me, and I see an astronaut in the audience here today, and some other future space explorers. What excites the youth? Well, if you're very young, it's dinosaurs and space. And it's truly space, I think, that we're trying to connect our humanity with something that's much larger than us and make sense of ourselves here on Earth and here in our solar system. And there's hundreds of solar systems now that we know about. So it's mind-blowing, I guess, is the best way to think about it. And that's kind of what gets people excited about it.
Thanks, Amy. I agree 100%. That's beautiful. Amy.
I think that like mankind is just programmed to explore, right? You want to know what's around the corner, what's over the hill, what's in the next country, what's across the sea. We've always been explorers. And so space is just the next frontier. It's this big, wide open space we can explore. We can go here and there and the next place, and every place is new and interesting and fascinating and kind of like challenges our assumptions about the universe, right? We're always discovering things we didn't expect, and it leads us to ask more questions and want to go further and go back, and it's just so exciting to get out and explore.
Yes. I've not given you a chance.
Well, I think they said it very well. And I think it's inspiring to think outside ourselves and to, I used to have a colleague when I first started in this business who would talk about the Hubble images and how inspiring they were and how it makes you feel really, really small and really kind of apart from the universe. But then when you actually flip it around and think about all the planets around other stars and that there could be life elsewhere, and almost certainly there is, that in fact we are a part of the universe, not apart from it. And to be able to explore that connection is very inspiring.
Thank you. Folks, I'm just going to ask one more question, and then I'm going to open it up for the audience. So have a think about any questions you want to ask. I think my last one to everybody is there's huge changes happening over the next decade in space exploration. Yeah. So what are you most excited about? What do you think we're going to be in 10 years' time? And let's have Susie first.
Well, I think one of the big impacts for the Deep Space Network will be the Artemis program, humans back to the moon and then to Mars. And it's all going to be supported primarily through the Deep Space Network, at least initially. So, and right here in Canberra or Tittenbilla, if you want to get more specific, is where the action's going to be. That's the place you're going to want to be a part of that. Get humans back to to the moon again, and then on to Mars is the grand plan. So that's sort of the near term, I think, space program. And I'm always excited just by missions like Clipper, right? Let's look for water. Let's look for life. Let's see what we can find. And so Clipper's got to be very exciting. Uranus probe is another one they're talking about right now. I'll share one more little anecdote. When I left college, I graduated with my undergrad degree, had a few different job offers, but the one that I took was the one at JPL on Voyager going to Uranus. Why did I take that? It's the only mission that was going to go to Uranus. It was not the highest paying job. It's still the only mission that's flown by Uranus.
January 1980.
Which is actually a sad statement to sit up here and say, but we need to continue the planetary exploration, and there's a lot that we don't know. Every time we fly a mission, we learn more about what we don't know, right? What are the questions? We answer a few questions and we get way more questions to be answered in the future. So I'm looking forward to what's to have in the space program, and I'm excited by all of it.
Thank you. Amy.
I think, like Susie said, like having astronauts out, getting them to the moon, getting them beyond the moon to Mars, I mean, I think that's going to be a huge focus. It's very exciting. It's very inspirational. And of course, they'll be doing, amazing science along the way, but it's very exciting to see the astronauts going back to the moon. And then the other thing, you saw the cat video up there, returned by optical comm system. I think there's just a thirst for more and more science data. So I think a lot of the missions are going to be producing more science data. They're going to want to get more science data to the ground, and one of those ways might be optical comm. So excited to see where optical comm goes in the next decade, and whether or not we're getting videos back from Mars of the astronauts.
And the cat.
And the cat.
And the cat that's on Mars with the astronauts.
Yeah. I mean, it's a good choice because I think, what is it? Cats make up about a third of the internet. So
That's right. No, cat had to be a cat video, right? Yeah, absolutely. In terms of what is going to be happening in 10 years, I'm really excited to say, I have no earthly idea. Because, yes, we will, we'll be at Europa with Clipper, we'll be, continuing to do science missions. I think humans will be back on the moon. By then, the first woman will have walked on the moon. What a concept. It's time, which is great. But if you think about where we were 10 years ago versus today, the whole rise of the commercial space industry, and especially of new entrants in that industry, it has changed so dramatically. I don't think any of us would have predicted that Elon Musk would be launching 100 times this year with SpaceX, and he will, right? And I think in addition to NASA and our international partners, again, pushing the envelope in deep space exploration, what that means is it's sort of opening up near Earth space for everybody. And so think about how 10 years ago, if things go well, how many, right now, I don't know, a few hundred people have flown in space. How many thousands of people might have flown in space by 10 years from now? It's just going to change the game when more people have the overview effect, see the Earth from space. I don't think we can fully predict yet how that's going to change. And to me, that's one of the very exciting things, is that while we will continue to push the frontiers and the boundaries, there are going to be changes that we cannot even imagine yet.
Lovely. Thank you. Okay, so questions from the audience. Yes? Just 1 second, she'll bring
a microphone.
Mic for you.
Yes, all right.
What are the pros and cons of working at JPL?
Cons.
Pros and cons. You two have worked there longer than I have, so you should really.
Well, I think you've heard a lot of the pros, right? You get to be involved with these one-of-the-kind, inspirational, super exciting missions. One of the cons has disappeared. It used to be we didn't have enough parking spaces. But now with remote work, a couple days a week, the car problem has been solved, has an outcome of telework. There's really not a lot of cons. I think some days you come to the office and you're feeling down, but then you go get a cup of coffee and you talk to the barista and they find out you work for NASA or you work for JPL, and they get all excited and ask you tons of questions about what you do and how it's so exciting to them that you're, out studying space, and that just makes you feel good about your job. So there's really not a downside to working at JPL.
And you definitely should.
I think one of the really cool things about JPL is all the different things that you can work on in a career at JPL. I've worked on telecom on the spacecraft side. I worked on instruments. I worked testing. I'm now working in the DSN, right? Like, you can have all sorts of different experiences, and all the folks that work there are just amazingly brilliant at what they do. And so it's exciting to walk around and talk to the other people in the area where you don't work, and to learn about the things that they're working on, the things they're building, the science they're doing. It's just a really exciting place to be. And cons, sometimes we have too many meetings.
Too many what?
Meetings.
Oh, meetings.
Are you even able to comment on cons of working at JPL? I mean, is that, yes,
No,
as director?
there are no cons, it's perfect. No, it's wonderful. I mean, so look, it's a large organization and it's a mature organization at this point. Large, mature organizations develop bureaucracy. It's sort of a law of physics, it feels like. And so, I think that's the question is, where does that help us dare mighty things, and where does it hinder it? And how do we kind of continue to try and make sure that we can unleash the brilliant minds and more importantly, the incredible teams that come together to make amazing things happen. And look, it's, we're part of a federal agency, which means there's politics and there's always budget drama, and some of those things are not always fun. So there are definite challenges too, but the thing I love most about it is it's mission, like it's truly mission driven, right? This is about discovering previously unknown things in space, and it is that mission that unites us, that brings us together, and that those bonds are very strong, and it's about doing things that haven't been done before. And so again, that makes it inherently challenging, which is great, and sometimes also difficult to explain. Why does it cost so much, and why does it, when you're trying to do something really nearly impossible that's never been done before, we don't always know how much that's going to cost at the beginning, right? So there are definite interesting challenges of doing it within the confines of recognizing that we're spending taxpayer dollars, right? And so, of course, we have to be very responsible with how we go about that.
Another question at the front.
Hi. Oh, she's running down. She's running
Just
down.
one sec.
No, it's good.
It's furthest away, isn't it?
Yes.
That's better. Thank you so much for visiting Australia and sharing your experiences with us. I'm curious, with the amazing advancement in our scientific knowledges, have you found new scientific professions emerging, or is it the case that what we currently have are just evolving in pace with that?
No, it's definitely, sort of the emergence of AI is a great example, right? So, we have people at JPL working on automation and artificial intelligence for satellites. Our Mars rovers, for example, so Perseverance recently got sort of a brain update, or software update really, but it used to be when Penny and I would plan the days for Curiosity, we'd have to plan down to the second of every single thing we wanted the rover to do. Now for Perseverance, they sort of say, well, here are the 5 different things we want you to do today. You figure out which order you want to do it, right? Like they're giving the rover much more smarts and much more autonomy to figure out how to do its work. That doesn't just happen, but that's because of continued advancements in, in capability of both hardware and software. Quantum is another huge area that has the potential to revolutionize how we do sensing and instrumentation from space. So when you see sort of broader scientific trends, it's often true that there is an application in the space arena that we try and take advantage of. So that's quite exciting. And then the last thing I'll say is the sort of whole field, and we sort of call it astrobiology, right? The idea of sort of life in the universe. When we first started in this business, not a lot of people talked about it. Like everybody was sort of interested in it, but they weren't sure it was really kind of allowed to talk about this as a scientific question. And that has completely changed, right? That we are now really put it in many ways at the center of our investigation of the universe to try and understand our place, life's place in the universe. Is it a natural part of the evolution of stars and planets and solar systems? Is life sort of almost a inevitable outcome of that or not? And we still don't know the answer to that. And now there's a whole generation of scientists who really that's what drives them. And it's so exciting to see.
I was at the back and then...
and then you can like
closer.
move the microphone to the
thanks
next
for your
person.
talk. That's great. I keep hearing that this Artemis project's like a bottomless bucket that NASA keeps tipping money into. Being pessimistic, how do you think that's going to affect your work in the next 10 years, either, with missions that people have spent a decade working up getting cancelled or delayed or scaled back to be almost budget-type missions?
Well, that sounds like it's one for me.
You are the boss, so.
Good question, and an astute one, right? And it's certainly true that historically, if you look at NASA, in the height of Apollo, similar things happened, where it's really safety is so paramount when you have human beings on top of the rocket and involved in the missions that sometimes they take longer and cost more than expected. So especially in a time when the overall budget is very tight, if this is a priority of the agency, then it is impacting. And if you follow NASA budgets, and I really hope none of you do, but if you do, you would see that in fact science has been cut in order to help make sure that we stay focused on Artemis. And again, it's not a massive cut. It's not, it's not the end of the world and we will be okay. But so these, these priority making decisions do have to happen. That being said, I think it's really important that we get out of just having humans going round and round the earth. Like NASA needs to continue to lead the way with partners to be a spacefaring nation and really get out beyond. So I think it's an important goal. I think it's a tight budget time, and so that means there are some impacts. That being said, you saw my family portrait chart, right? I mean, there are many, many incredible scientific missions happening. It is the NASA spends $7.5 billion a year on its science program. That's an extraordinary investment, and we're really fortunate to have all of the incredible missions we have. And we got to keep working to make sure we get to keep having more.
So what was the journey to becoming like part of JPL? Like how did you get there, and what things do you is it more likely to study that will get you there?
So I did not know what an engineer was before I went to college, but I really liked taking things apart and figuring out how and whether or not I could put them back together. And I liked math. And so as I was getting ready to graduate and go off to college, I had some people suggest, well, why don't you look at engineering, because you like math and you like to take things apart and put them back together again. And so engineering is such a huge field that there are so many options and so many different things that you can do in engineering. And so I studied electrical engineering. I thought I was going to go work in the music industry in Los Angeles, and I ended up at JPL instead. And I think it's been a much better home for me. But yeah, I think pursue engineering, math, science. I think all of those things are a great way to contribute to science or to get involved in the space program.
Yeah, and I would agree with what Amy said, but I loved math. I had teachers in high school that really encouraged going into a STEM field. I think, this is a funny little story, but we had a young physics teacher when I was in high school, and his class had more females in it than males, I think. So just his looks got to a lot of females in my high school to study physics. But I also, when I talk about what it takes to work at JPL, it's important to be a good communicator. So and as Laurie mentioned, we work in teams. So it's important to be a good communicator. It's important to be able to work in a team environment. You're not going to be able to survive at JPL if you're just working on your computer all by yourself. That's not what JPL does. So having creative ideas, being able to communicate those creative ideas to others, that's important too, as well as the math and the science. And, JPL has business people. We have HR specialists. So we're not just 100% engineers and scientists. And we're looking for the best people in those areas as well.
Lawyers and professional communicators. We have all sorts of team members that it really does. It takes a village, right, to explore space, and so that's why we added that word together to the end of Dare Mighty Things, because it really is all about that team. So, and then if you really are interested in working at JPL, summer internships are a good thing to think about, right? So come and work as a student, come and work for part of the year there, and we can take non-US students in certain roles to do that. So you can go on our website and look at that and apply, and definitely welcome that, because we hire a lot of people out of our internship programs.
Actually, just to follow up on what Laurie said, there's, if you're an undergrad and I think a PhD student in Australia, there are organized intern programs with JPL and other NASA sites. Mm-hmm. So that is a program that is available. Absolutely. Want to put
you can also stay here and work in space here in Australia.
You can if we need, yeah. But yes.
What is the most challenging thing you've ever done at JPL?
Raise your hand. I can't see who's talking.
All the way at the back.
Oh,
at the top.
Hi.
Yep.
Hey, all right, balcony people. What is the most challenging thing you've ever done at JPL? The commute has terrible traffic. No, no, that's not true. Wow, the hardest thing. Do you know?
I can jump in for myself.
You should tell the Voyager.
Well, about the recent Voyager story? Oh, okay.
It
was pretty hard, yeah. Okay, so in November, we lost communications with Voyager 1, and it wasn't so much that we lost the communications, but we couldn't understand what it was telling us. And we spent the next 6 months reestablishing communications with a spacecraft. And I say that because it's definitely a team effort. It took the telecom organization, the people that really know communications well, to determine that, yes, the spacecraft is actually talking to you, you just don't understand what it's saying. And we diagnosed that to one particular computer out of 3 that's on the spacecraft, that it had an error in the memory. It had some corrupted memory. And then the next group came along and said, okay, we need to rewrite that memory. So we did a software upgrade to the spacecraft that is 15 billion miles away from us, and reprogrammed it so it then sent the data back down, and we understood it, and it was like it didn't miss a beat. Boom. Just like it was operating normally, with a few like minor tweaks, but definitely a challenge, definitely that something that was stressful. You know, the site here for the DSN in Australia is the only site that communicates with both Voyager 1 and Voyager 2 from an uplink standpoint. So the folks that work at that site, they're part of the team too. They're part of the Voyager team. They make it happen. Just the amount of acknowledgements from around the world that, yes, the spacecraft is back. Thank you so much. The well wishes we get. That's what makes it worth it. You know, just knowing that people are rooting for you and are excited about it. And that is one of the most difficult things we've done from that sense for that project. So.
I think one of the hardest things to do in space is landing on Mars. It is just, it's really tough. For the longest time, fully 2 out of 3 of the things we sent to Mars failed, right? And so that is a place that we've kind of learned now. And so all of the Mars rovers that we've landed and driven around on the surface, those are huge accomplishments. The fact that we've now landed 7 times in a row successfully is quite a good streak. So yeah, I think that's a good one too.
Good.
Yeah.
Yes.
Up there?
I think last question at the top.
In JPL, what do you think is the best job aside from your job?
Oh, the best job. What is the best job? They're all so good.
Well, I was going to say, I think Amy talked about how you can do many different things over the course of your career. So there's probably not one best job, but you know, I obviously enjoy what I do. I enjoy the colleagues that I work with. I enjoy the ability to switch positions at JPL, to move around, to learn new things, work with new colleagues. So the best job, it's not Laurie's job.
That's true.
But yeah, it's pretty close to mine. Maybe it's my deputy. So there you go. My deputy has the best job. So
Because he works for you.
because he works for me. Yes, exactly.
Amy, what about you?
Yeah, I think it's also very difficult to pick the best job. I think one of the really coolest thing, though, is that you can design something on paper, right? You can build up the schematics, and then you can go and you can help actually build the physical thing, and then you can take that and you can go help integrate it onto a spacecraft and test it out in the full system on the ground, and then you can go and operate it once it launches and it's up in space. So you can be part of any one piece of that life cycle of the instrument on a spacecraft, or you can potentially go from all the way from the concept early on all the way through operations and making scientific discoveries. So I think there's lots of opportunities at JPL to have really cool jobs.
Yeah, and there are certain people that like certain parts of that. Like if you really like building stuff, you might want to stay focused on, delivering those, that hardware. I will tell you my favorite part of it is at the beginning when you have that sort of clean sheet of paper and you're trying to imagine something new. And we actually have kind of a formal place at the lab where we try and enable teams to do that. It's called the Foundry, where you throw people in this room that's like full of whiteboards, floor to ceiling, where you can, create new ideas. And the Psyche spacecraft, actually, that's on its way to the metal asteroid, it started right there. They had a crazy idea, and they refined it over time and proposed it to NASA, and NASA selected it to fly, and we built it, and now it's flying. But there's something really exciting about the early days of a mission when every idea is crazy and you wake up every morning and think, oh, here's 3 reasons that's never going to work. And then you figure out those 3 things, and then you move on to the next 3 problems, and you just solve problems one at a time until you're flying, And I love the early days of these things when you're really in kind of scrappy brainstorming mode and just trying to figure out whether there's anything there or not.
I think that's lovely. Thank you. So I'm going to wrap up the panel now and thank speakers and panelists and recognize that they've actually just got off a plane. They've been flying for 30 hours. So I think that's pretty good going. So if we join me in thanking And I also want to thank JPL and NASA, CSIRO and the Canberra Deep Space Communications Complex, the Academy of Science for hosting. Special thanks to Glenn Nagel from the Canberra Deep Space Communications Complex for making this event happen. I've had a wonderful evening. I hope you have as well. That was lovely.
Have a great night. Yeah.